Today we're starting our new topic of combinatorics. But before we can look into counting techniques, we first want to just do a general overview of set notation. So if we have a set S, which is a collection of objects, and all of the objects in that set are called elements of the set. So for instance, if our set is the even numbers between 1 and 20 inclusive, S could be written a number of ways. 3 examples of this would be a list, a rule, and a Venn diagram. So writing it out as a list would just be as simple as separating all of the even numbers by commas, and then surrounding them by curly brackets, which are generally used for our set notation. So writing these all out, we get all the even numbers from 2 to 20 inclusive. If we were instead to write this as a rule, we want to define it by values of n, where n satisfies an equation. So n in this case is going to be equal to 2 times r. R is just a pronumeral that we've set up. It's going to be all of the numbers between 1 and 10. So all of the natural numbers between 1 and 10, if you multiply those by 2, they're going to become all the even numbers between 2 and 20 inclusive. If we were to draw that as a Venn diagram, we'd get this set S. Everything in that circle are even numbers. Everything out of that circle are odd numbers. And then that makes up the universal set, which in this case is going to be all the numbers from 1 to 20 inclusive. The complement of S. Now this is complement with an E. We're not talking about, oh, you look very nice today. We're talking about things that complete the universal set in this instance. The complement of S, written as S prime or S dash, is the set of all things not an S. So in our case, that's going to be all of these numbers outside of the circle, which is also all of the odd numbers. So that's going to be 1, 3, 5, 7, all the way up to 19. The complete set of objects being considered is called the universal set. And that's notated by this Greek letter here. So for example, our universal set in this case is going to be equal to all of the numbers from 1 to 20. So continuing that on, we'd get to 19, 20. Consider a second set T, which instead of being even numbers are multiples of 3 between 1 and 20. So those are going to be 3, 6, 9, 12, 15, and 18. So the set S and T can be combined. If we look at this, we're actually missing a number. See if you can find which one it is. It is 20 in the set S. So we were missing all of the numbers. I assume because maybe at one stage this wasn't inclusive of 20, but in our example it is. So when looking at this Venn diagram, we have 3 bits of information we can get. It's everything that's in S, everything that's in T, everything that's in between it, and I guess we have a 4th bit of information, which is everything that's outside of those 2 circles. So when looking at all of the elements in either S or T or both, that's going to be everything in these 2 circles. We call that the union. So S union T is going to be equal to everything except 1, 5, 7, 11, 13, 17, and 19. So that's going to be 2, 3, 4, not 5, sorry. We're going to have 6. We're going to have 8. We're going to have 9, 10, not 11, but 12, 14. We will have 15 because it's a multiple of 3. 16, not 17, 18, and not 19, but we will have 20. So that's just looking at what satisfies both of those rules. The intersection of S and T is just looking at the three numbers in the middle here, 6, 12, and 18. So in our case, they would be items that satisfy both being even and being a multiple of 3. So that's written as S intersect T, so it's like an upside down U, and in our case, that's going to be 6, 12, and 18. So the number of elements in S is given by n of S, which in our case is going to be all the numbers from 2 to 20 that are even, and that's going to be 10 items, 10 elements. If we wanted to find out how many elements are in both S and T, we'd use what's called the inclusion-exclusion principle. So the number of the union of S and T is equal to, it's the number of things in the circle S, the number of things in circle T, but you'll notice if we add those two things together, we have an issue. We've added these 3 items in the center twice. So we actually have to subtract one instance of the intersection to accommodate for that. So this is the inclusion-exclusion principle. We include both sets and then we exclude the intersection between the sets. If we have 3 sets, so imagine some third set, let's call it R, the intersection of these, the union of these, to find the number of each of them, or the union of them, we first have to find the number of each of them, but then we've added their overlaps too many times, so we have to subtract the intersection between each pair. So S intersect T, S intersect R, and R intersect T. But if we look at this as a drawing, we're going to see what we've just done is we've added all of this, we've added all of this, and we've added all of this. We've then subtracted one section of the overlap, subtracted another section of the overlap, and subtracted a third section of the overlap, which means this part in the center is actually not accounted for anymore. So this purple part that I'm shading here has not been accounted for because we added it 3 times and then subtracted it 3 times. So we actually have to add that back in. So that will be the adding the intersection of all 3 sets. And that is our inclusion-exclusion principle for 3 sets. Okay, for example 1, we're now looking at R, S, and T, each with their own set of rules, each looking at the universal set of 15 to 30 inclusive. They have to be divisible by 2 to be in set R, divisible by 3 to be in set S, and divisible by 5 to be in set T. So I'm going to construct my Venn diagram so that we can populate it together, and then we'll answer the other 2 questions. Okay, so now I've got my 3 circles together. We're going to label each of them a different letter to represent a different set. Now, generally when looking at this, I prefer to start with what they have in common first, and then fill in the rest of the stuff later. So what would be in this intersection right here is something that's divisible by 2, 3, and 5 that's between 15 and 30. So if we multiply these 3 numbers together, we're going to get 2 times 3 is 6, times 5 is 30. The only number would be multiples of 30. Now we stop at 30, so we're only going to have one number in the center, which is 30. When looking at the intersection of R and S, that's going to be numbers that have multiples of 6. So in our case, it's not going to be 6 because we start at 15. It's actually just going to be 18. That's the only multiple of 6. Oh, sorry, there are many multiples of 6. That's the first one. So we've got 18. We're also going to have 24, and then 30 is in the center there. So when looking at the intersection of R and T, that's going to be numbers that are divisible by 2 and 5. So that's going to be our multiples of 10. So we skip over 10 because it's not in our universal set. We just have 20 there. And then the last one is the intersection of S and T. That's multiples of 15. So it's going to be 15, and then 30 is in the center there. So now we need to populate all of the other numbers. So we know that the other even numbers are going to be in set R. So 15, we then have 16 is our first even number, 18 is already accounted for, we're then going to have 20, which is accounted for, 22 is next, 24 has been accounted for, 26 hasn't, and 28 hasn't. So those are the 4 numbers that would be in set R. We do the same thing for S. So 15 has been accounted for, the next one would be 18, that's been accounted for, the next one would be 21, 24 is accounted for, we'd also write 27, and then 30 is accounted for. And lastly, we've got the multiples of 5. So 15 and 20 are accounted for, all we're missing is 25. So now we have to go through and see what are the numbers that aren't allocated in these 3 sets. So we've got 15, 16, we do not have 17 in a set, so we write it outside. 18, we don't have 19. 20, 21, 22, we don't have 23. 24, 25, 26, 27, 28, and we don't have 29. So there's some sort of property about these 4 numbers that mean that by how we're constructing the set, they're never going to be in a set. And that's because all of these numbers are prime. So if we're looking at divisible by different integers, then we're never going to have prime numbers in any of these sets because they are only divisible by themselves and 1. So I guess the only instance that they would be in a set is if the divisible number was 17 or 19 or 23. Then they would be included as the first number in that set. Okay, part B is asking us to use the diagram to evaluate the union of R, S, and T. Then we're going to apply the inclusion-exclusion principle and see if we got the same number. So when finding the number of things in the union, all I'm doing, that should be RUST, or RUSUT, we're just counting all the things that are in the circle. Faster way to do that is going to be recognizing that there are 15 numbers between 15 and 13, and there are 4 numbers not included. So we should be getting 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I was wrong there, and that's because I wasn't counting 15 as being included. So there's actually 16 numbers between 15 and 30 when looking at an inclusive. So part C is applying the inclusion-exclusion principle. So same process, we're looking for the number in this union, but now we're splitting it into number in S plus number in T plus number in R minus the number in the intersect of all of the pairs but then adding back the intersect of all 3 pairs. So in that case, the number in S is 1, 2, 3, 4, 5, 6, plus the number in T is 4, plus the number in R is 1, 2, 3, 4, 5, 6, 7, 8. The number in the intersection of S and T is going to be 2 numbers. The number in the intersection of S and R is going to be 3 numbers. The number in the intersection of R and T is going to be 2 numbers. And then we have to add back the 1 that we lost in that process. So we get 10, 18, minus 2 is 16, minus 3 is 13, minus 2 is 11, plus 1 is 12. So we got the same answer, which is good. That's what we were looking for. Okay. Counting techniques allows us to determine the number of ways an activity can occur. This allows us to calculate the probability of an event. So the probability of event, let's say probability of the event A, is equal to the number of times A happens over the number of times everything happens. So that's the complete set. Also, so when looking at the complete set in terms of counting techniques, we also call that the sample space. So the sample space is all possible outcomes. Different types of counting techniques are employed depending on whether order is important. When order is important, this is called an arrangement or a permutation. When order is not important, it is called a selection or a combination. So what this means is that you have been lied to your entire life. Combination locks should actually be called permutation locks because the order of the combination matters. So, applying addition and multiplication principles. Consider this scenario. You are driving from Brisbane to Rockhampton and can take any one of 4 different roads. And then driving from Rockhampton to Townsville, there are 3 different roads you can take. How many different routes can you take in driving from Brisbane to Townsville? So we can represent this as an image. Here are our 3 nodes, and we can take 4 different paths. 1, 2, 3, 4. 4 different paths from Brisbane to Rockhampton, and then 3 different paths from Rockhampton to Townsville. So we could list all of these possible outcomes. R1, which is the first road. So the road to Rockhampton, and then the first road to Townsville. We could then have R2, T1, R3, T1, R4, T1, and then R2, T1, R1, T2, R2, T2, R3, T2, R4, T2, and then R1, T3, and this continues. But what we notice from this array that we've created is that it's going to be 3 by 4. For every road that takes us to Rockhampton, there are 3 roads that could take us to Townsville. So the way we can do this is using the multiplication principle. So it's going to be 3 times 4, which equals 12 ways. So the multiplication principle, if there are n ways of performing operation A and m ways of performing operation B, then there are going to be n times m ways of performing A and B in the order AB. So let's look at example 2 here now. So A, B, C, D, and E, where order is important. So that means A, B is different to BA. Calculate the number of ways this can be done, and then determine the probability that the first letter will be a C. So we could write out all of the different options, or we could just use the multiplication principle. So multiplication principle would give us 5 ways of choosing the first letter. So that could be A, B, C, D, or E. But we can't then take the same letter the second time. So if I take A out, it's no longer in that set of 5 letters. So my only options are B, C, D, and E for the second letter. So this is going to give us 20 different options for the set of 5 letters. I'll leave you to write out all of those options, but it's going to start with A, B, A, C, A, D, A, E, and then you just change the first letter to the next one, and so on. There's a logical order to it, but that gives us 20 possible outcomes. So what happens in part B if we lock our first letter in as a C and then give you the option for the second letter? Well, instead of there being 20 ways, I now really only have 4 ways, right? Because the only letters that I can choose for this second slot is going to be A, B, D, or E. So that's 4 different ways. But I'm not asked how many ways are there. I'm asked the probability. So probability that C is first is going to be equal to the number of ways C is first over the entire set, the sample space, if you will. So this is going to be 4 out of 20, which is a 1 in 5 chance. So there's a 1 in 5 chance that C is going to be the first number picked, first letter picked, rather. So let's instead calculate how many ways an arrangement of 5 numbers can be chosen from 1, 2, 3, 4, 5, and 6. Now we have to infer ourselves whether order matters here. So you have to consider, is 12 the same as 21? Well, obviously not. 12 is 9 less in value than 21. This is much more significant than the order of, say, counters. Like if I chose a red counter and then a blue counter, that could be the same in the palm of my hands as a blue counter than a red counter. But in the case of numbers, the order is important because it changes the value of my outcome. So how many different ways can we arrange 5 numbers choosing from 1 to 6? So I have 5 places for my 6 numbers. How many options do I have for the first one? Well, I could choose 1, I could choose 2, 3, 4, 5, or 6. So I have 6 options for my first number. But once I've taken one of those numbers out of the pool, I can't take it again. So if I take 4 out, I can't take 4 out a second time. So how many options do I have left? Well, I only have 5 options left there. Then after that, 4, then 3, and then 2. And then there'll be 1 number left in the pool that I haven't taken out. Determine the number of ways. To do that, all we're doing is multiplying these 5 numbers together. So 30 times 4 times 3 times 2, that's going to give us 720 different ways. If we're asked to determine the probability of the number ending with a 4, we're locking in that final number that we can choose. So I have to reconsider how my other 4 numbers can be chosen because of that. So I don't have 6 options for number 1 anymore. I only have 5. Then I have 4 options, then 3 options, then 2 options. And I only have 1 way that I can choose the 4. So multiplying these together, we are going to get 120 different ways. But I'm not asked for the number of ways, I'm asked for the probability. So the probability that 4 is last is going to equal 120 over 720, which is equal to 1 in 6. So, consider another scenario. You're traveling from Brisbane to either Sydney or Adelaide. There are 4 ways of traveling from Brisbane to Sydney and 3 ways of traveling from Brisbane to Adelaide. How many different ways can you travel to either Sydney or Adelaide? So, let's draw our nodes again, but this time we're starting from the middle and we've got the choice of either Sydney or Adelaide. So I have 3 options to take me from Brisbane to Adelaide, 1, 2, 3. And I have 4 ways of travelling to Sydney, 1, 2, 3, 4. Am I going to multiply these 2 numbers together or add them? Well, if I take one of these options to Adelaide, so I travel from Brisbane to Adelaide, I then don't have a second choice. My trip is complete. So I'm not multiplying these together. It's not paths branching out from different options. These are what we call mutually exclusive. So the 2 options don't rely on each other. So it's actually just the 3 options that take me to Adelaide plus the 4 options that take me to Sydney for a total of 7 options. So this is called the addition principle. If there are n ways of performing an action and m ways of performing an action, then there are n plus m ways of performing A or B. So let's look at example 4. 1 or 2 letters are to be chosen from the set of 6 letters A, B, C, D, E, and F. Assuming order is important, calculate the number of ways to choose 2 letters. So, number of ways to choose 2 letters is going to be based off our blocks that we were looking at earlier. I have 1, 2, 3, 4, 5, 6 different options from A to F. And then I have one less option for the second number, so that is going to be a total of 30. For part B, the number of ways of choosing 1 or 2 letters. So I've used my multiplication principle for part A, but now I'll be using my addition principle for part B. So I know that for 2 letters, there are 30 ways. For 1 letter, there's going to be 6 ways. So all I have to do is add these 2 values together. There's going to be 36 ways to choose either 1 letter or 2 letters. Let's look at a slightly harder example here. Oscar's Cafe offers a choice of 3 starters, 9 main courses, and 4 desserts. How many choices of 3-course meals are available? So, looking at this, we have 3 starters to choose from, we have 9 main courses to choose from, and 4 dessert courses to choose from. This is going to be 12 times 9, which is 108 ways. So 108 different choices for your starter, main, and dessert. Part B is asking us, how many choices of starter and main course meals are offered? So that's just starters and mains. So that's just going to be 3 times 9, which is 27 options. Part C. How many choices of meals comprising a main course and a dessert are offered? So that's going to be 9 times 4, 9 mains, 4 desserts. That's going to be 36 options we can take. Part D. How many choices of 2 or 3-course meals are available, assuming that a main course is always ordered? So that's going to be given by the number of starters and mains plus the number of mains and desserts plus the number of starters, mains, and desserts. Well, that's what we've calculated in our first 3 instances. So for part D of this, we're just adding our answers to A, B, and C. So starters and mains was part B, so that's 27 plus 36 plus 108, which gives us a total of 171 different ways to order 2 or 3-course meals. Part E, if one of the starter options is chicken wings and one of the mains is grilled fish, determine the probability of choosing chicken wings and grilled fish in a 3-course meal. So 3-course meal, we first need to determine what is the number of options. Well, first of all, let's set up our probability equation. So the probability of chicken wings, let's just call it CW, and grilled fish, GF, is going to be the number of options, including those 2, over the entire set. So if it's a 3-course meal, our denominator is going to be 108, but we have to determine what is this number of chicken wings and grilled fish. So what we're doing there is we're locking in a starter of chicken wings, so that's locked in. We're locking in a main of grilled fish, so the only thing that could change is our dessert. So 4 options for desserts, that's our only option for the numerator. So simplifying this out, we get there is a 1 in 27 chance. If you just blindly picked, like pointing at the menu with your eyes closed, but you locked in those first 2, you'd have a 1 in 27 chance of getting those first 2. Sorry, they wouldn't be locked in, But if you closed your eyes and just pointed randomly at the menu, there'd be a 1 in 27 chance that you would get chicken wings and grilled fish. So that finishes off combinatorics for today. We will be moving on to factorials and permutations for the next episode.